Okay, pre-calculus, this actually says Unit 2, but it is actually Unit 7, Day 3 notes. Unit 7. And we are going to practice graphing rational functions today. So before we start, I just want to show you one thing. I found this online. This is a great reminder. Every time you do this, okay, if you just cancel out a term in the numerator and a term in the denominator, a kitten dies. And I love this because I get this. What this is trying to get across is this is a serious, serious mistake. The numerator and the denominator are each, those are numbers. We don't know what they are, but you can't cross out part of a number. So for example, this is wrong. For example, and if I show you with numbers, you'll understand. Okay? So I know 4 plus 2 is 6, 6 divided by 2 is 3. The value of the first expression up here is going to be 3. Down here, 4 times 2 is 8. 8 divided by 2 is 4. The value of this bottom expression is going to be 4. Okay? If I cancel these 2's out, that's going to be 4. That is legal. It's a legal move. I cannot cancel those 2's out because this 2, there's a number up here. And it's not being multiplied by anything else. So I can't cross out part of a number. So that is why you cannot cross out part of a number. You're going to see this over and over and over again. So if you see, me draw this, okay, there you go. There's a dead cat. Okay, so knowing that, let us move on. So most of this is going to be review. So a rational function is a function in the form of p of x over q of x, where p and q are polynomial functions and the degree of q is greater than 0. Okay, so first we're going to quickly review on how to find the domain of each of these rational functions. So if I go ahead and start with the first one, if I take a look at the denominator here, I know that x cannot be negative 5 because at x equals negative 5, that makes the denominator 0. And anything over 0 is undefined and we're not going to be able to graph it. So there's going to be an asymptote there. So the domain for this function is everything, all real numbers except negative 5. And you can write that in interval notation as I've written here. For number 2, when I go ahead and set this denominator equal to 0, now I've got an x squared equals 4, so x can be plus or minus 2, or can't be, I should say, plus or minus 2. So we have to not include 2 and negative 2 in our domain. For C, when I go ahead and set this denominator equal to 0, when is x squared going to be equal to negative 1? Well, x is plus or minus I. We're not graphing i's. We're on the x and y axis. So really, we can plug in any value we want from negative infinity to positive infinity. So that domain is everything from negative infinity to positive infinity, all real numbers because we're not including imaginary. And the last one, if I go ahead and set this denominator equal to 0, where can the denominator be 0? That's at x equals negative 1. So x cannot be equal to negative 1 because we've got a vertical asymptote there, which we are going to talk about right here. Now this is a review. The first two, the horizontal and vertical asymptotes, are review from Algebra 2. However, I don't know if they teach the oblique asymptotes in 2 trig. I know they don't in Algebra 2. But a horizontal asymptote is basically anywhere where the denominator, I was thinking vertical. Horizontal is as x is approaching infinity. So if you've got a graph and x is going this way, x is approaching infinity, or x is approaching negative infinity, if the rational function r of x approaches a fixed number L where the line y equals L is the asymptote. Okay, so if the graph is going up and it's here we go. So if you have a horizontal, for example, if you've got a horizontal asymptote at, I don't know, y equals negative 2, okay, somewhere like that. Okay, your graph is, as it's approaching infinity, is going to be approaching that value. Okay, and as it's approaching negative infinity, it might be approaching it this way. Who knows? It could be also approaching it from this direction, okay, depending on what graph you've got. For vertical asymptotes, let's say we got a vertical asymptote at x equals 2, right here, okay? Your graph is going to be approaching your vertical asymptote. So as normally you have like a horizontal and a vertical. So let's say you've got a horizontal and a vertical. It'll be approaching it this way and this way, for example. Okay. And oblique asymptotes are slanted. Okay. So when an asymptote is neither horizontal or vertical, we call it an oblique, or sometimes we call it a slant asymptote. Those two names are used interchangeably. Like horizontal asymptotes, the graph of R may intersect the oblique asymptote. Okay. It can, because this is really, the asymptotes are about end behavior, so it can cross the asymptote. Yes, right here, where it only describes the end behavior of the graph, and we'll get into that. So let's go to an example. And I don't know how long this video is going to be. It might be longer than 15 minutes. All right, so if the degree of P, the numerator, is equal to the degree of Q in the denominator, then all you have to do to find the horizontal asymptote is divide. Divide the leading coefficient of P by the leading coefficient of Q. Okay. Now, if the degree is, so for example, let's say it's 3x squared over 2x squared. Okay. We know that right there, there's your horizontal asymptote, because the degree is 2 for each of those. Since the degree is equal in P and Q, the leading coefficient, that's just where the horizontal asymptote will be at y equals 3/2. Okay. Now, if the degree of P is less than the degree of Q, then the horizontal asymptote is at y equals 0. And this is new. If the degree of P is greater than the degree of Q, and it should only be by a factor of 1 as of right now, then there is an oblique or a slanted asymptote that can be found by dividing the polynomial P by Q, and that's where we get into synthetic or long division. So let's move on to vertical asymptotes. We kind of did this for the domain. You're going to write the equation in lowest terms by factoring and dividing away the common factors. So anything that's a removable discontinuity, okay, any factors that are the same, we're going to cancel them out. Then you just set the remaining denominator equal to 0, and that's how you find it. Okay, so for example number 1, when I go ahead and the first step is factor this numerator, I see if I pull a 3 out, if I GCF out a 3, I don't have a factor in the numerator and a factor in the denominator that cancels. So I'm going to have no whole. So that means I'm going to write no whole, none. Okay, now the next thing I usually like to do is the vertical asymptotes are so simple. I know I'm going to have a vertical asymptote where the denominator can be equal to 0. So that means that vertical asymptote is going to be at x equals 2, because 2 minus 2 makes that denominator 0. Can't have a 0 in the denominator. So I've got my vertical asymptote. Let's figure out the horizontal asymptote. So if I look at the degree of the numerator versus the degree of the denominator, looks the same to me. So the leading coefficients will be 3 over 1. So my horizontal asymptote will be at y equals 3. It's probably best if I go ahead and just plot those now. So I'm going to go ahead and plot them in a very light yellow, because they're not part of the graph, and that's just what I like to do. So x equals 2. There's a vertical asymptote, and y equals 3. Now again, you can do this in the same color, but I kind of like to do it in a lighter color because it's not part of the graph. So now the graph is going to be approaching each. All we need now is a couple points, and then we can graph. Is the graph going to be here? Is the graph going to be here? That's really all we need. So we go ahead and, we still have to find the X-Intercept and the Y-Intercept. Okay, so now what is the X-Intercept? Okay, I'm just going to explain this like you've never heard of an X-Intercept before. Okay, X-Intercept is where the graph intersects the X-axis, which makes every single point on this line y equals 0. So I'm going to put in 0 for y and see what I get for x. So my f of x is my y. So I go ahead and plug in 0 there. Okay, well now if I think of this as a proportion and I cross multiply, 0 times x minus 2 is just going to give me 0. So really it doesn't matter the denominator. All it matters is solving the numerator. 0 equals 3x plus 9. What value of x makes this true? And that's going to be -3. So there is an x-intercept at -3, 0. Plot that point. Is that right? No. There we go. Okay, now the y-intercept. Okay, I know it's up here, but I'm just going to work down here. The y-intercept is along the x-axis. So that is, I'm going to plug in 0 for x and see what I get for y. Now we don't have to do this, but I'm just going to do it anyway. So you can see these two terms are going to end up being 0. So really the y-intercept is at -9/2. So when x is 0, y is -9/2. And then you just have to kind of estimate that graph. So 9/2 is 4.5, -4.5, right? So I'm going to graph, I cannot even find the axis. This is so hard to read. Okay, 1, 2, 3, 4.5. So it's about right there. Okay, well now I've got 2 points. So I know that my graph is approaching these asymptotes. So I can go ahead and draw my graph over here, approaching the horizontal and vertical asymptotes. Since the degree, and this is kind of interesting and it's not in our curriculum, but since we only have one, the multiplicity of the denominator, x minus 2 is only 1, your graph is only going to be approaching this vertical asymptote from opposite directions. So we know the graph is going to be up here rather than down here. If it was down here, we'd have to have in the denominator x minus 2 squared or something like that. Okay. Okay, so now I probably just like to have maybe 1 point up here so I could plot it. So 1 point would be, I don't know, we could do f of 3 and I get 18. That's off the grid. F of 4 and I get 10.5. F of 5 and I get 8. Okay, good enough. So f of 5, is that 5? And I get 8. Good enough. There you go. There's your graph. For the domain, it's everything except for the x value that we can't use, which is the asymptote. So that's going to be from -infinity up to, but not including 2, in union with 2 to infinity. And the range is everything except for the horizontal asymptote. So -infinity up to 3, but not including 3, in union with 3 to infinity. All right, I'm going to go ahead and start this one, but it looks like I won't be able to finish this example in this video. I'll have to move on to the second video. But if I go ahead and just start with factoring, I'm going to notice that I've got a factor in the numerator and a factor in the denominator that cancels. So here, more simplified, our expression is x plus 3 over x plus 2, which immediately tells us the vertical asymptote is going to be at x equals -2. And the degree is the same in the numerator and the denominator, so that's just 1 over 1. That's the horizontal asymptote is at y equals 1. The removable discontinuity is going to be at 3 something, which I'll show you coming up here in just a second. We'll figure out how to get that y value. And the y-intercept, and when you plug in 0 for x, you get 9/6 for y, simplified 0, 3/2. And then the x-intercept, when you plug in 0 for y, you get -3 for x. So let's go ahead and plot those points, and then I'm going to move on to the next video. So I've got -3, 0. I've got 0, 3/2. So that's 1.5. I've got some asymptotes at y equals 1. And I've got a vertical asymptote at x equals -2. I'm going to go ahead and stop right there.